Hello everyone, it's a pleasure to meet you. I'm delighted and honored to share our work, titled Patrol, Privacy-Oriented Pruning for Collaborative Inference Against Model Inversion Attack with you. Our research is centered around defending against model inversion attacks during large-scale deep neural network inferences. First, we will show the background of our study. Given the escalating memory and computation demands of deep neural networks, deploying the entire networks on a resource-constrained edge device has become increasingly challenging. Large-scale DNNs impose a substantial burden on edge devices in terms of computation and memory costs. In response to this challenge, collaborative inference has emerged as a valuable solution in recent years. It divides the large-scale DNN into two partitions and deploys at the edge and the cloud. Leveraging the computational capabilities of powerful cloud, partition computations can be offloaded to alleviate the constraints on the edge device. Nevertheless, collaborative inference encounters a significant challenge in the form of model inversion attacks. These attacks seek to reconstruct confidential information from input data by exploiting intermediate outputs during the inference process. An attacker may target two potential vulnerabilities, the first being the transmission process from the edge model to the cloud model, and the second being the cloud itself, particularly if cloud zone is not deemed trustworthy. Since the edge device faces computational constraints, encryption methods like homomorphic encryption are unsuitable in this scenario. This limitation serves as a motivation behind our work. In the next section, we will show our basic idea for defense under edge device constraint. Our inspiration stems from an observation in prior research. Specifically, the performance of model inversion attacks diminishes when targeting a later layer compared to a previous layer. The images showcased on this slide were extracted by a model inversion attacker from the intermediate output of the collaborative inference model. Evidently, the reconstructed image quality from a later layer, indicating the deployment of more layers on the edge model, is inferior to that from a previous layer of a model. Building upon this observation, we implement the pruning method to compress the collaborative inference model. This compression enables the accommodation of more neural network layers on the edge side, contributing to enhanced privacy preservation. In the following section, we will present all our methodology and techniques in our defense. To begin, I'll provide an overview of our design. We introduce a privacy-oriented pruning method called Patrol with the goal of accommodating more layers on the edge model. Within Patrol, we incorporate two key components, libshaft regularization and adversarial reconstruction training to enforce task-specific features at intermediate outputs. This approach aims to preserve inference accuracy while mitigating the impact of task-irrelevant but sensitive features. Subsequently, I'll introduce more details about pruning, libshaft regularization, and adversarial reconstruction training components in Patrol. The pruning component aims to facilitate the accommodation of more layers on the edge model. We introduce a trainable softmask app, access the importance of specific structures, for these structures like channels or blocks in the model, by scaling their output. Less crucial structures are pruned based on a pruning threshold tau, where the structure is pruned if the mask value is less than or equal to the threshold. Govern sparsity and minimize prediction loss. We apply the L1 norm and L2 norm together with two hyperparameters lambda1 and lambda2 throughout the pruning process. We incorporate libshaft regularization to diminish the stability of model inversion attacks and amplify their reconstruction errors. A small perturbation, small delta, is applied to a block's input to observe the resulting change in the block's output, allowing us to estimate the libshaft constant. The libshaft loss is computed as the sum of all blocks' libshaft constants. Our optimization problem is formulated to minimize both Lipschitz loss and the prediction loss of the target model. A Lipschitz loss close to zero indicates a more unstable reconstruction process. Adversarial reconstruction training is designed to mislead model inversion attackers and safeguard input data privacy. We create a surrogate model, simulating an imagery attacker's attempt to extract raw input data from the intermediate output. The surrogate model endeavors to minimize the L2 norm distance between its reconstructed images and the actual input data, or this term the adversary loss. Conversely, we posit that the target network seeks to maximize the adversary loss. Hence, the optimization problem for the target model assumes a min-max game fashion, serving as a defense mechanism against the strongest model inversion attacks. And next, we will show our experiment settings and results. We address a real-world privacy-sensitive task, vehicle re-identification, which necessitates robust protection. Our experiments involve testing on two privacy datasets, the VRI and VRI wild datasets. Each dataset compresses a substantial number of vehicle images and car identities, with a significant amount of confidential information requiring a high level of protection. We deploy ResNet 18 as a target network, consisting 4 residual blocks and containing 2 residual layers. Our primary focus lies on 3 evaluation metrics, PSNR, SSIM, and L2 norm, to measure the quality of adversaries' reconstructed images. We assume the model inversion attacker possesses knowledge of model structure, training dataset, and input dimensions, and we evaluate both black box and white box attacks on patrol. We present the reconstruction performance of black box attacker on patrol, contrasting it with other methods. These methods include introducing noise to intermediate output, random drop-off of the intermediate output, random skip connection, adversarial training defense, and the target model without defense. Across the 3 subsets of VRI wild and the VRI dataset, patrol surpasses existing defense in terms of prediction accuracy and privacy preservation, as indicated by lower PSNR and SSIM metrics. From the adversary's reconstruction images, we can clearly recognize the reconstruction images from no defense model, but cannot recognize identities from reconstructed image under patrol defense. The notable degradation in the quality of reconstructed images after applying patrol serves as compelling evidence of its effectiveness in defending against model inversion attacks. We also deploy the L2 norm metric as an auxiliary metric to measure the effectiveness of patrol. We only use VRI dataset in this experiment. The results depicted in figure as PSNR and SSIM metrics. In this experiment, we evaluate patrol against a robust white box model inversion attacker. The white box attacker's performance on a model without any defense surpasses the black box attacker. However, on the contrary to this, our defense method demonstrates greater success in thwarting white box attacker. Well, this proves that patrol can defend the white box model inversion attacks. To assess the defense effectiveness of adversarial training and Lipschitz regularization, we compare the performance of various defense strategies. The results present in the table demonstrate that the combination of the adversarial reconstruction training and Lipschitz regularization yields a superior defense compared to use any one component with pruning, or only use pruning. At last, I'll make a short conclusion for our paper. In this paper, we propose Patrol, a privacy-oriented pruning for collaborative inference. Patrol pushes more layers to the edge without largely degrading prediction accuracy and efficiency. To remove some privacy-sensitive parameters, we introduce Lipschitz regularization and adversarial reconstruction training in Patrol. And on the real-world dataset for vehicle re-identification task, Patrol can successfully protect collaborative inference against model inversion attacks. Thank you for listening.